what I kind of want to go over. What I want to make sure we go over in chapter 2 is the master theorem, and covering things like that, as well as evaluating some if I give you an algorithm, I want you to try to evaluate what it is using the master's theorem. But we're not going to. So just a couple of asides and a bit of pedagogical reasoning. So we're using this textbook. It's a great textbook. In some case, but I was speaking with, Tony Hughes, who's the professor on main campus who normally teaches this course, and he's like, oh yeah, but I would prefer sometimes something a bit more mathematically rigorous. And me, having used this as an undergrad, I'm like, why? And having read through it, I can see why, because a lot of his explanations are, do you see why this is? Or we can clearly see that it is this, and jumping from there to there, it doesn't lead, it asks you to make some leaps by yourself. Now, that being said, the book that's typically used in this class is this chunky brick. It is a giant tome. It is a bludgeoning instrument. That is how big this book is. It is on par with some epic fantasy in terms of its size. CLRS. So I like to say that this book tells you everything. This book tells you everything you need to know. This book tells you everything you want to know. And The Art of Computer Programming by Knuth, who started writing it in 1968 and it's still not finished, tells you everything you didn't think you needed to know. It is very extensive, even though it's not finished, because it's split up into volumes, and he's still working on it. In fact, what's funny is that when he was trying to get the second edition of Volume 2 done, it required to be typeset, but the typesetting technology that he was using was no longer available, so he instead went off on an entirely different tangent in 1978 and spent 8 years working on TeX, a typesetting system, which is what's used for a lot of scientific papers, because let me tell you, when I was still in college and before then, it was a pain in the butt to get Microsoft Word working on on making nice typeset mathematical equations. It's great these days, but oh my God, was it a travesty earlier? But we use this one. Why? Because it's relatively cheap, and it's very, very light and easy for me to carry around. And thus, okay, so where does that come with? So anyway, while you were all doing this, I was working on a brand new sorting algorithm, okay? Brand new, obviously not, but hey, it's a good story. Okay, so, and I've created this algorithm, okay? And let me translate it for you, okay? Takes in a list, and its default parameters are I is equal to 0, j is equal to none. What does that mean? Those are basically the start and end points of a subarray, okay, of a sublist. Make sense? So basically this denotes the area that I'm trying to sort between this range. And if I is not, if we don't specify an ending range, then we just use the ending, so from the beginning to the end. And the way this sorting algorithm works is I say, okay, if the beginning and the end of the subarray are out of order, swap them. Okay? So check if the beginning of the array, if the end of the array is smaller than the beginning of the array, I swap them. Okay? And then, as long as there's more than three things three or more things to swap, I sort the first two-thirds of the array, then I sort the second two-thirds of the array, and then I sort the first two-thirds of the array. And now here comes the issue. If I were to come to you, fresh out of data structures, and ask you, what is the runtime of this algorithm? You're like, not quite sure, because it's kind of weird, because we're doing one swap at a time, and then we have 3 recursive calls, including one that does that kind of goes over the same amount, but you need that third recursive call to make sure that that everything that gets sorted by the second 2/3 gets sorted again. This does work, by the way. It is a valid sorting algorithm. It does work. We can test it on some numbers. So print stooge sort as this is called. It should work. I mean, I grabbed it from Rosetta Code, and grabbing stuff from the internet never goes wrong. Okay, and as you can see, it does work indeed. Mainly, I wanted to make sure that these things were correct. It's not a particular. So the issue is that using the tools we have with for loops and the like, and what we've learned, we don't really have any good tools for analyzing this one. So we're going to start by taking a look at analyzing. So what we're going to do today is that we're going to analyze merge sort, and then we're going to kind of get our bearings, our theoretical bearings from there. Okay. I'm eschewing the slides for a bit, by the way, because this I think works better without the slides. Okay. So how does merge sort work again? Right? We've all done merge sort at some point. Wait. First off, this is yours. Second off, where's mine? Where's my pen? Like, seriously, I pack these things up to use them, and then when it's time to use them, there they are. Okay. Hey, I thought it was out of batteries, but apparently it still has an erg of life left in it, so I'm going to use it for all it's worth. Okay, so merge sort so I printed this off from Duke, but basically we can define merge sort this way. Or actually, why am I writing it out? My handwriting's so much, my typing is so much better. Def, abstractly it is, and I'm going to call it outline because basically this isn't going to be working implementation of code. This is just going to take in a list, and it's going to take in a start point and an end point, right? Okay, and the idea here is that start is on the left and end is going to be on the right? And they're both going to be integers. So we figure out what the middle is by saying that's equal to, let's see, left, the start. You don't have to write this down. We all know what this is. Start plus the end, divide by 2, and we should do integer division here, because that's what we kind of assume in these kind of situations, integer division. Okay, so start minus the end, divide by 2. And then we do if start is less than end, right? Okay, if start is that's less than the end. In other words, if we haven't crossed any streams or anything yet that would invalidate this, then what we're going to do is we're going to merge sort the left from the start to the middle. Then we're going to merge sort from the middle plus 1 to the end. And then we're going to combine them, right? We're going to merge them. Right, left. We're going to combine them using the list, the middle. Sorry, let's go do start, middle, and so we know where we want to combine them. Merge is undeclared here, but I showed you the method for doing it last time. And I mean, if you're really interested in it, again, Rosetta Code has like 1.5 million implementations of it. If you need to watch an animation of how it works again, right? It's fairly straightforward. By the way, again, Wikipedia is like the best when it comes to like sorting algorithms. It really is. Because it has all these wonderful animations. And as we can see here, that worst case proof, that is always n log n. It is always n log n. Okay? So there's ways to make it like a bit more efficient and stuff like that. Bottom up versus top down doesn't really matter. The question is, what is the runtime of this algorithm? And we know that merge sort, okay? We know from experience that merge sort is from Wikipedia, we say it's an n log n. But I mean, like, actually, let's go ahead and figure it out from the recurrence, okay? What does merge sort do, right? Merge sort, again, says we're going to merge sort half the list. We're going to merge sort half the list. And then we're going to merge them together, okay? So the time it takes... So we're going to use a couple of facts here. First, the time it takes to do merge sort is the time it takes for merge, we went over that last time. It takes O of n. So whatever we do in terms of solving our subproblems, to recombine them, it takes O of n time, right? Right? Merge is an O of n operation. Just if you take two sorted lists and combine them, right? So what we're going to be doing is that we have and then merge sort itself we do merge sort again, but on a problem half the size. So we have t over 2 plus t over 2. Sorry, t of n over 2. Sorry. Writing and talking at the same time, very difficult. Okay, so we're going to just simplify this, right? So this is merge 1, merge left, merge right. They both take the same amount of time, assuming everything is split evenly, and that's probably the case. It's going to be good for our analysis anyway. So that's 2 t of n over 2. All right. So for the sake of expediency, I'm going to just go ahead and erase the O of n over here and just leave it with n, okay? Just for the sake of doing the algebra a bit easier, okay? Now, the other thing we need to keep in mind as we're going on is that t of size 1, how long does it take to sort something and merge something of size 1? 1. Takes one step, right? It's done. We check and it's done, right? So if we could reframe this in the terms of number of t of of subproblems of size 1 we had to do, we can rephrase that as that. Then we can take this and transform it into the actual runtime. Does that make sense? So let's think about this. Well, how do we do that? Well, we need to expand this. Okay, and that's where the trick comes in. So we need 2, and I'm gonna go ahead and rewrite this just a bit. So give me a second. I'm gonna use a different color for a second. 2. So we have 2 t of n over 2 operations. So over here that becomes. So each of those n over 2 operations, right? Each of those halves, they split into quarters, right? You following what I'm saying here? We merge, if we have an entire array, right, we need to merge sort the left half and merge sort the right half, and then those have their own left half and right half, right? So I'm going to just rewrite this as t of 2. Let me go ahead and rewrite this. 2 t to the fourth, sorry, two t n over 4 operations plus n over 2 plus n. So all I've done is taken this one and I've applied the recurrence ID, and I basically used the recurrence formula inside my own program, inside my own formula. See how it is 2, we had a problem of n over 2, so that can be split into two n over 4 operations, right? And then to combine an n over 2 operation, you have to do an n over 2 time to merge them, right? So notice over here what we've got. We've got 2. So we've got in 2t of n, 2 operations of, 2 subproblems of half the size, okay? Those half-size problems can be split into 2 quarter-size problems. And so now if we expand that out again, 2 times, so if we expand this out and, distribute this 2, we get 4 times 4t n over 4, okay? And then plus 2n. Where did I get the 2n? Well, the 2, again, distributing to the n over 2 and then combining them. Make sense? Okay, let's go a bit further. Let's do this once more.
Won't that just be n then?
You'll see in a second. 4, 2, and now we'll do t. This is going to be 2 t to the n over 8 plus n over 4 to put them together plus 2n, right? So I've taken what I've done is I've taken this, right, and turned it into that. Made sense? Right. A quarter can be split into 2/8, and it takes a quarter of that time to merge them. Which, if we distribute this, if we do the math again, right? If we do the math again, okay, then we are going to say that is equal to 8/8 operations. Okay, plus n 4, so this would be 3 of n. Okay, so now I guess the next step, we have 2 more steps to do. The first is what it would be plus 3 of n. So now the question is, what do we expand t over 8 into? T n over 8 into?
T n over
16? How many n over 16?
2.
Yep, 2.
T n
Yep, t of n over 16 plus
n over 8.
yep, n over 8. And now if we distribute that, what does that turn into? 16t. So yeah, 16t over n over 16, right? And how much n now? 4n. So the question becomes, how deep does this go? Well, it's a tree. How deep is this tree? Well, sorry, let me rephrase that. Let's let k be the depth of this tree. How deep is the tree? So yeah, so log of, well, log base 2, everything's in log base 2.
K of k?
No, k, we're trying to figure out the formula for k. All right, how deep is this? So let me rephrase that, okay? So let me go ahead and draw again, because so we've got this, then we split it into 2 halves, and then we split these into quarters, right? And at what point can we stop? When these are equal to size 1, right? So at what point, how deep does this have to go to get to size 1? Think of merge sort for a second. How deep does that, how many levels of recursion does it go? Because each layer takes O of n to recombine, right? So this takes n time to recombine, this takes n time to, how many n operations are there in merge sort's runtime?
N into N.
And over
What is merge sort's runtime again?
and over
So how many levels of n operations are there?
1.
log n.
Log n, there we go. There's log n levels, right? There's going to be log n levels. If I have 8 items to sort, merge sort goes 3 layers deep. If I have 16 items to sort, merge sort goes 4 levels deep. Make sense? Because that's how many times I have to split it up. Okay. So this is equal to what? K is equal to log of n. Now, why am I doing that? Because now I can rewrite this formula. Okay? Because right now we're going up by powers of 2 right over here. Okay? So if I want to put this in terms of equal to how many T of 1 operations are there? They're going to be, well, how many, so this kept double, so the 2 in front kept doubling, okay? How many times, how big does this 2 get? What's the exponent of 2? How many layers deep does it go? How deep does the layer go? It goes K layers deep, right? So what is that? So what is K? Log base 2 of n plus, and then this gets to be K of n. Oh, we can simplify that, can't we?
Yeah,
Yeah.
it should be, I feel like it's just n.
That is just n. Logarithm rules are just so we have n operations plus K of n over here. What is K again?
Log n.
Yep, K is log n, so it's, yep. And so the T of, so the total runtime over here
1 plus log N.
is T of n is equal to n plus log n times n. So it's kind of easy to see that when we derived. But the idea here, but this is the general idea you'll be seeing for what the master theorem does for us, okay? What the master theorem does for us is that it gives us a formula, it gives us an answer to what is the runtime for all this formula. Because it's obvious for this one, kind of, because, the deriving of that was obvious for this one. Not so obvious for Stooge sort, which, if I were to write it, right, Stooge sort comes out to T of n is equal to 3, it gets split into 2 subproblems, each of which is n is equal to 2/3 of n, right? Two n over 3, right? And then it has, I think that it just basically doesn't have a recombine operation. It just, each time it just has a single operation that basically swaps it, right? A constant time operation. In terms of n, I guess it would be n to the 0th power over there, right? So we're going to use, so for the master, so we'll come back to that in a second because let's go ahead and write what we call the master theorem. Now the book uses a much easier version of the master theorem, a much more specific version. It does mention in the footnotes that there's, and you're going to see in your slides, there's a much more like symbol-heavy version of the master theorem. But for the problems of solving these kind of recurrences, these ones, then it works for this. And regardless, the formula is still the same. which is T of n is equal to, a recurrence relation is of this type. T of n is equal to A times T of n over B. And it does use the ceiling symbol over here, but I'm going to assume, but for sake of easy analysis right now, we're going to assume that it's a power of 2 plus O of n to the dth power. That is your master theorem. You will sometimes see it written as, oh, this is so annoying that, stop it, I want to draw. T of n is equal to a t of n over b, so same so far, plus f of n. You'll sometimes see it written as that, as the more general form, but this is the one your book's using, so that's the one we're going to use. Okay? So what does that do for us? Well, it gives us a couple of well, your book has basically given that, so it says given a few things. Given that A is bigger than 0, B is bigger than 1. In other words, given that that it actually divides stuff into subproblems, okay? Okay, and the book has proof. There's proofs for these over here, but honestly, this is a summer course, and I want to try to get through this as possible, and I don't want to bore you to death with the proof. But we'll see it in action. The slides go over the proof. I know, do it? Oh. Point being is what can we do? It says basically that you've got 3 possibilities. The runtime is either, the runtime for this is n to the dth power. It's n to the dth power if D is greater than log B of A. Okay? This is going to be a bit weird. It's n to the dth power log n if D is equal to log B of A. Okay? And last one, what do you guess the last condition is going to be before I even write what it's going to be?
Smaller.
Yeah, smaller than log B sub A. Okay? And that is, it's going to be, and it's got this weird runtime, n to the log A of B, if it's smaller. Okay? So what does this really mean? So it means that basically in this case, in this top case, this means that basically that a lot of the work goes into the recombining, less in the subproblems, more in the root of the problem, right? Where the answer isn't that big in the root. Okay? The next one is that there is the next one says basically that the root and the subproblems are kind of, that the root and the recombining and the subproblems, they're kind of evenly balanced. So in other words, those subproblems, the bottom of it, the leaf as we'll see, those are balanced against the overall thing of combining. And let's take a second, take a look at merge sort for a second. That was, A was 2 and B was 2, right? A was 2 and B was 2, right? For merge sort, merge sort was 2t to the n over 2 plus 0 to the first power, right? In those cases, A was equal to 2, B was equal to 2, D was equal to 1, and so log B of A was 2, log base 2 of 2 is 1, right?
Yeah.
So that was 1 is equal to 1 for merge sort. So we were able to say, so we can just look at this chart without having to do the analysis and say that merge sort is n to the dth power. D was 1, so n log n. Make sense?
is that formula?
Yep, this is essentially a formula for everything. This is a formula for runtime, okay? With 3 possible answers, okay? And the reason I brought up Stooge sort is because it's got a very interesting runtime, as we've been saying. So Stooge sort, if we go back to that, has this power, okay? So it has this runtime, and that's why I wrote n is equal to the 0th power, because it's just got one step, right? So T of n, so in this case, A is equal to 3, because there's 3 subproblems. B is the size of each subproblem. Well, yep, it's going to be 3 over 2, right? Even though it's 2/3, you know. Even though it reduces it into 2/3, so to divide by 2/3 is like multiplying by let's see, in order to multiply by 2/3, we have to divide by 3 over 2. It's a bit weird, clunky, but work with me. And then D is 0. Now, okay, without having to act, so that, sorry, D is equal to 0. So we were doing, so it's log B of A. So this is saying, so we are doing 0 is less than, okay, log 1.5, for just ease of writing it for me, okay, of 3. Now, we know this is true even without calculating this. This is some number, okay? So we'll just leave it in that awful format for right now, okay? And we'll save that because Stooge sort does not have a clean runtime. It does not. So that brings us to this case where it is n to the log A of B power, meaning that it is n to the log 1.5 of 3 power.
There's something wrong.
So,
Can you go back to the formula? Like, is the formula wrong or the answer is wrong? Because formula says log A of B.
oh, yes. I was, sorry. B, A. Again, the talking and writing at the same time. It's not, it's,
Yeah, no problem.
no worries. I am not infallible. Okay. So we've got this runtime. So, by the way, let's just go ahead and figure out what that would be. Actually, I'm not going to bother figuring out what it's going to be. Stooge sort says it's log to convert it to base 2, by the way. So we can convert this into base 2, by the way, by doing a change of base, which is log of 3 over log of 1.5, where b is the base of whatever logarithm we want, right? Log base 2 in this case. So that's how they got to this runtime, which is approximately n to the 2.7 and a lot of other trailing digits.
That's not good.
It's not a good, no. This exists solely to be analyzed by the master theorem. It is a pedagogical algorithm. Okay? But for the most part, for these kind of recurrences where you can turn it into a subproblem like that, it works. Let's go ahead and take a look at binary search for a second, okay? Binary search. Binary search, we don't even have to look at the code for binary search, I don't think we have, or at least I don't think so, right? Binary search says basically look for an item. If it's less than the, look at the middle item. If it's less than the item, go to the left half. If it's greater than the item, go to the right half, right? That's T of, and then search that half, and only that half. And so that's the runtime for that, right?
Yeah.
Right? That's split it, if you've got n problems, split it in half, and that only takes one operation to check which half you should go to. So in this case, A is equal to 1, B is equal to 2, d is equal to 0 again. So again, that gives us n to the, so this gives us n to the, let's see, log base 2 of 1. Let's see. Did that give me the right to runtime? Because I don't think so. Hold on a second. May have messed up somewhere. Oh, D is less than B of A. B of A, 2 runtime. A is 1. What's log base 2 of 1? Should be 0. So that would give me constant time, right? No. Oh, wait, no. Ooh, no. D is 0. I messed up. D is 0, and we got to. I skipped a step. We got to compare it. I got too eager. We compare it, and we find that D is equal to log B of A. Right? I was skipping a step, which means we're comparing it, and 0 is equal to 0, which means we use the middle formula, which is n to the dth power, which is constant, log n. So the formula works for that. Now, it's a bit trickier to use it on something like sequential search, which if we were to define it recursively, or selection sort. So actually, let's go ahead and see. So yeah, selection sort. Let's define selection sort. Selection sort, if we were to define it recursively, is equal to T of n minus 1 plus O of n. Okay, where did I get that? Selection sort looks for the smallest item, moves it into the first index, and then does the same for the remaining items, which is a subarray of size n minus 1, right? So it doesn't, for here, this kind of breaks on over here, and I believe you would have to use kind of the other formula, because again, that's not really the kind of, because this is not divide and conquer. The recurrence relation, this rule that we're using right over here, this is great because it works for because this works for our divide and conquer algorithms, because this is what divide and conquer looks like. However, in this case, with this kind of algorithm, it's not too hard to see that this will be n plus n minus 1 plus n minus 2 plus n minus 3 amount of time, which basically means that this comes to be O of n squared. So you can see it in these things, but primarily what we're looking at is O of n algorithms. So let's go ahead and open up the slides now. Okay. Oh, that is not what I wanted. And that's not what I wanted. Those are solutions. Slides. So we've got divide and conquer. So, by the way, the slides do go out of order of your textbook. That's personally fine, I find. But this is where we were going into with merge sort. I should also point out that we are measuring these sorting algorithms in terms of comparisons again, because comparisons are more expensive than exchanges, right? There's two operations that go into sorting algorithms: comparing two items to see if they're in order, and then swapping them, right? That's not always true, though, as some of the homework exercises in this textbook point out. There are sorting algorithms that work without comparing things, like radix sort. So just keep that in mind. So what we see is that this algorithm, so this is the tree for our, this is the tree that basically we worked out mathematically instead of drawing a tree, right? You've got T of n splitting up into two half-size operations. Each half-size operation turns into quarters. Each of those turns into eighths. So there's going to be n layers. The total runtime is n log n. This is just kind of proof by drawing the recursion tree. proof by induction. They start, here, again, that shows that if it worked for size t, if it worked for t of 1, it's going to work for n. Assume it works for n, then do n plus 1. Okay? So the idea here, though, is that there are a bunch of different proofs we can do to this. Now, what's interesting is that your textbook does have these wonderful asides in gray over here. And this is one of them that basically points out that that merge sort is kind of helps see that this is as optimal as it gets for sorting. That n log n is a lower bound for sorting. You can't do any better in this because if let's go ahead and consider you're going to be sorting these items, and every so often you're going to end up at a leaf for 3 items, and basically ask, okay, for these 3 items, this is the decision tree to see if what order those 3 items should be in. Okay, what order are they in? Okay, and for those 3 items, this is 3. It takes 3 comparisons, which is exactly the worst case. And this is kind of where you're going to get to when you do merge sort. And it's basically pointing out that this is showing that merge sort is optimal, that it has that it says the sorting, best you can do for sorting is that sorting is lower bounded by n log n. It is omega n log n. And they go into a lot of stuff. But there are, it is worth pointing out that this is only if you're using one processor, right? If you're using multiple processors, you can actually speed this up quite a bit. That is a completely different class, though. What I mean, like basically figuring out how to split things up between multiple processors. Like we've figured out a while ago how to optimally sort 16 items with like a parallel merge sort. Yep. And as they point out, it's only useful for algorithms that use comparisons. So here's the more formal definition that they use for the divide and conquer algorithms, okay, for this here, which is A, which is the number of subproblems, B is the factor by which we decrease those subproblems, and F of n is not just the time to recombine them, but also if it takes time to split up those subproblems, we work it in. K is they use as log B n levels, right? K is the number of levels that we get, just like we were using. A of I is the number of subproblems you have at a certain depth, and n divided by b to the ith power is the number of subproblems you have at a certain depth. So here is a sorting algorithm that is, sorry, not a sorting algorithm, but an algorithm that is T of n, three subproblems, each of a half size, and it takes n size to combine them all. Okay? So here on this work, we see that, on the top level, it just takes O of n time to recombine them because that's what it says for T of n. But for each of the subproblems, we split it into 3 problems of T of n over 2, and then the work of recombining these subproblems is more than it was at the work to be done at this second level is more to be done at the top level. You see that? Because we've got 3 problems, each of which take n over 2 time to recombine their subproblems. And it gets worse as we go on until we split it down to the lowest level, which is going to be 3 to the log base 2 of n. That's how many levels we have, with n over, and each being, of size 1. This is how we get size 1. And we can use some nice funky math over here to, this may look familiar to you for those of you, for problem 0.2 in your homework with that formula for the geometric series. To show that what you get is 3 to the n log base 2 of 3 minus 2n for the runtime. Which if we do our math, right, let's go ahead and take a moment though, an aside, to use the formula that we learned. right? So D is 1, right? D is equal to 1, right? A is equal to 3, B is equal to 2 in this case, right? Using our formula, we can, or the formula presented in the textbook for divide and conquer algorithms, right? We can safely say that this is that we have, log B of A, log base 2 of 3, that is greater than 1, right? Because log base 2 of 2 is 1, log base 2 of 4 is 2, so this is safely between 1 and 2, so it's greater than that. So it's greater than D, which means it's our third case, which is O of n to the log 2 of 3 power, which is exactly what they have, because if we scroll down, right, n to the log base 2 of 3. This is what I mean by it's a bottom-heavy tree. See how basically it takes more work each level to do the recombining than it does to recombine at the top level. When these things are balanced, yeah, that's great. It takes exactly as much time on the top level. See, it's here you have n, 2 subproblems, each of a half to recombine them, and so on and so forth. It's balanced out, so it gets n log n. And then here, if it's top heavy on the root, three problems of n to the 5th size. We see that so here, this is one we haven't seen before, right? Here, A is equal to 3, B is equal to 4. So that means log of 4 of 3. That's less than 1, ain't it? Yeah. So ain't it? I mean, yeah, we use such formal language in this formal mathematics class. So D is 5. 5 is greater than whatever this nonsense is, so we're going to use the other. So we use our first case, which is we use O of n to the 5th power. Notice that they're writing big theta here, and we're using big O. Again, we're using a simplified kind of formula that works for these divide and conquer algorithms, because here's the more general cases they have, right? So here's case 1, how they write case 1. That f of n, if f of n is O of n to the k minus e, or sorry, what is that, eta? K minus eta for some constant eta greater than 0, then T of n is eta is big theta n to the k. So it's showing in this case, hey, it can be described as k. Sorry, we can f the function f of n, which is n over here, can be described in terms of log base 2 of 3 minus some eta, which makes sense to me. But I mean, again, it's not as clean as it. I think there's other things where basically here this one simply says, hey, if this is our middle case where it's kind of equal, n to the kth log p. Now you can see why I like our definition's a bit better, right? This is more formal stuff. And then it has a lower bound, and then if it has some eta, again, we have f of n. And what it says over here is that it requires some constant factor, and also that it has a regularity condition. What does that mean like that? That means that the master theorem is kind of worthless if our runtime looks like this. And we're cosine of n. Sorry, let me go ahead and erase and redraw that a bit better. N times 2 minus cosine of n. Okay? And notice that this term, based on how, as n it goes to infinity, it's going to constantly vary because that's what cosine does, right? So it's going to be very wavy. It doesn't really help us for our analysis here. So anyway,
So may we have a break?
sure. Sorry, so there's the Master's theorem. Again, your textbook goes into a much better detail of it.
Which one?
What?
Is it this one or the other?
The algorithms textbook goes into, I mean, so the other so Wikipedia and the like, they go into much more detailed about the proof and the other stuff, but this recurrence, but the book is much more applicable for everything we're doing in this class. That's what's important, right? I mean, sure, if you want to get into the heavy mathematical theory and like that kind of and theoretical stuff,